Welcome everyone. In today's video, we will talk about differentiation and derivative of function. We said a function f is said to be differentiable at x0 if the derivative f derivative x0 exists. In other words, we had two limit definitions for this, right? If those limits were existing, then we will say there's a derivative at that point. If we say a function is differentiable, we mean it is differentiable at every number. And the process of finding the derivative of function is called differentiation. We learned two limits to evaluate the derivatives. And of course, we're not going to use those limits every single time because we have faster methods, right? So let's look at the faster methods we have to evaluate the derivatives or differentiate these functions. First rule is derivative of a constant, c. So if you differentiate c, and let's say the c is in the set of R, which is a real number, derivative of this is 0. How do we know this? I'm not gonna show all of these, but let's show some. So what was our definition? Fx plus h minus fx over h. And let fx be c, right? So this limit transforms into c minus c is equal over h. And inside of the limit is 0, so h approaches 0. And the function is 0, so 0. Our rule, derivative of x to the nth power is equal to n times x to the power of n minus 1, where n is a real number. We want to show this, right? So first of all, let's write this in limit of fx minus fa over x minus a as x approaches to a. What was this equal to? F derivative a, right? Derivative of fa. Fx is equal to x to the nth. Fa is equal to a to the nth. So this limit will be equal to supposed to a x to the n minus a to the n over x minus a. To cancel the x minus a, so we need to write x to the n minus a to the n in a different form, right? We need to take the x minus a out of this. So this will give us x to the n minus 1 plus x to the n minus 2a plus it will continue like this, plus x to the a, x times a to the n minus 2 plus a to the n minus 1. So now, I don't want to write all of these again, so I'm just gonna take it from here. This is over x minus a. Cancel these out. Limit x approach to a, x to the n minus 1 plus x to the n minus 2 times a plus x to the x times a to the n minus 2 plus a to the n minus 1. Plug the a's in. A to the n minus 1 plus a to the n minus 2a plus a to the a times a to the n minus 2 plus a to the n minus 1. And this will be equal to n times a to the n minus 1. Why? Because I get a to the n minus 1 from here. I get a to the n minus 1 from here, a to the a to the n minus 1 from here. How many are there? There's n of these, right? So n times a to the n minus 1. Let's try to do some examples of this so we get used to the applications of it too. Let's see. Let's say our fx is equal to 3x squared. Our fx is equal to 5x. Oh, we didn't learn the constant rule, right? So x squared, x cubed, let fx be x to the fifth power. I don't know. Let's evaluate the derivatives of this one by one. N goes to the front of the x, and minus 1 from our power, which is 1, so this is 2x. F derivative x is 3 goes to the front, right? 3x minus 1 from the power is 2, 3x squared. And last one is 5x to the fourth, because 5 goes forward, minus 1, 4, right? Constant rule. It is basically saying, like in limits, if there's a constant when we are evaluating derivative, we can take it out of the derivative. For example, fx is equal to 5x squared, right? When I evaluate the derivative, I can just keep the 5 out and evaluate the derivative of this x squared, so which gives us 10x. It's really simple to understand it, right? But of course, again, we need to see it, and to see it, we will use the limit rules we learned again. Let's start with let gx be equal to c times fx. Why do we do this? Is when we want to see that when we differentiate both sides, when we differentiate it, we want to see that we can keep the c out. So what is derivative of gx? Of course, limit h approaches to 0, gx plus h minus gx, and this is over h. What is gx plus h? Plug this in, so it is c times f x plus h minus, what is gx is equal to cfx. And this is over h. Now what can we do? We can continue to here. We can take this under the c parentheses, right? So under the c parentheses, fx plus h minus fx, and this is over h. Our limit rules, we learned the limit properties, right? We can take the c out, so this will give us c times limit h approaches to 0, fx plus h minus fx over h. And this is the definition of f derivative, right? So therefore, we will say this is equal to c times f derivative x. Let's do some simple examples. Let's evaluate the derivatives. Let's differentiate these functions. F derivative x is, we can just ignore the 6 at the beginning, right? So this will be derivative of x squared, and this will give us 6 times 2x, which is 12x. Derivative of 3x cubed. Okay, we can write this as derivative of x cubed multiplied with 3. If we evaluate the derivative by the power rule, 3 goes to the front, 3x squared, right? And now we multiply, if we multiply, 9x squared. So for this one, we know that root x means x to the power of 1 over 2, right? So we can write this as 2 times x to the 1 over 2 and derivative of this. Let's differentiate this. 1 over 2 will, we can ignore the 2, right? So like we can write it as x to the 1 over 2 derivative. Differentiate this, 1 over 2 x, 1 over 2 minus 1 is negative 1 over 2, right? And if you multiply these, 2 cancel out each other, so x to the power of negative 1 over 2. In other words, 1 over root x. Why it is, let's say the sum rules. If we have derivative of fx plus gx, we can write these separately and we can evaluate the derivative of each term. Let's see a really simple example before we show that this is correct. So for example, 5x squared plus 6x is equal to fx, right? It's asking the derivative of this. How do we evaluate it? We can evaluate the derivatives by for each term. So derivative of 5x squared is 10x, right? Because dropped 2 to the front, multiply 10, 2 minus 1 is 1. Plus derivative of x, power of this is 1, right? So we get 6, because 1 minus 1 is 0, so x to the 0 is 1. This was a really simple example, right? So now let's try to show that this is correct by our limit rules. Let's say our fx is equal to fx plus gx. We want to evaluate the derivative. We want to differentiate this fx, so this will give us fx plus h minus fx over h. From here, we get, what is this equal to? If we plug these, if we plug the x plus h in, we get fx plus h plus g x plus h minus fx minus gx, and this is over h. Now if you can see, when you group these together, you get the derivative of fx and gx, right? So now let's group these. Fx plus h minus fx over h plus, let's write it inside the limit, gx plus h minus gx. This is over h as well. We know that we can separate these by our limit properties, right? So we can write this as fx plus h minus fx over h plus limit of gx plus h minus gx over h as h approaches 0. And clearly, f derivative of x plus g derivative of x, right? Derivative of gx of x. So we know that, so we can say it holds. I'm just gonna leave it like that. The difference rule is the same with the sum rule. You can just differentiate each term and then subtract them from each other. So we will not prove this with the limit definition because it's really the same. You can do it by yourself. Now let's do some examples for what we learned until now. Let fx be 6x squared plus 7x plus 5x cubed plus 4. Evaluate the derivative, of course, differentiate this. 2 goes to the front, right? 12x is a constant. Minus derivative of x is 1, 7. Plus 3 goes to the front, 15x squared. And derivative of a constant is 0, so we will leave it like that. So we differentiated fx. Let's see another. 1 over x squared plus 1 over x cubed minus 1 over x to the 4th power plus root x. Alright, let's differentiate this now. Derivative of this is, first of all, let's start by writing this in a different form, right? Because I know that if it's something to the x power, like x to the 2nd power, 3rd power, I can work with it really easily by my power rule. But I really can't with this form. So you'll write this as x to the negative 2 plus x to the negative 3 minus x to the negative 4 plus, and for root x to the 1 over 2. Now I can differentiate this really easily. 2 goes to the front, negative 2x, minus 1 from the power, negative 3. Through negative 3 goes to the front, there's a plus, so this will be a negative minus sign. Negative x, subtract 1, negative 4, right? Negative 4 to the in front of the x, which gives us 4x. Negative 4, which gives us negative 5, plus 1 over 2, x to the negative 1 over 2. I will leave it like this. Derivative of the natural exponential function, derivative of e to the x gives itself again. No matter how many times you differentiate e to the x, you will get e to the x. So derivative of e to the x is e to the x. At what point On the curve, oh, I want to add something to this. We didn't write it? Okay, let's write it together then. Derivative of e to the mx, where m is a real number, will be equal to m times e to the mx, okay? Where m is a real number. At what point on the curve y is equal to e to the x is a tangent line parallel to the line y is equal to 2x? Okay, this requires some geometry knowledge, but if we have two lines and we want them to be parallel to each other, what do we need? They should have the same slope, right? So what is slope? Derivative. But we will not use the limit definition anymore because we know the faster ways. Derivative of this function is e to the x, right? And derivative of the other line we have, if we differentiate this, 2, right? I want these to be equal to each other. So e to the x is equal to 2. How do we find x from here? If we put ln to both sides, ln e to the x is equal to ln 2, and I can, by the rules of logarithm, x ln e is equal to ln 2. I know ln e is equal to 1, so x is equal to ln 2. It's asking the point, so yeah, what point? So we found our x point, but what is our y point? How will we find it? By plug it in here, right? Where y is equal to the x. E to the ln 2, these will cancel each out, so 2, right? So the point is ln 2 and 2.